Okay, so last time we formulated the key proposition. That given a single polynomial f, we consider the corresponding hypersurface, and its zeta function. And then the claim is that this zeta function is meromorphic. That is, it is a ratio, the ratio of two functions, f of t over g of t, and both of them are formal series converging everywhere. Okay, so we'll prove this, and the proof will. Well, yes. Sorry. Yes, this was very stupid on my part. Yes, thank you. Okay, so the proof somehow starts by induction in n in this dimension, and reduces the question to another counting problem. For h prime f that lies in gm to the power n. So we only count solutions that have not all non-zero coordinates. Okay, so this is notation for GM is A1 without zero. Multiplicative group. So that's why it's called G sub M. Okay, so we set zeta prime of HFT is in effect this is Z of H prime F T, and this is the exponential of the counting function n prime r t to the r over r as before, and n prime r is the cardinality of non-zero solutions. So we require that x I to the power q r, q to the r minus 1 is 1. Okay. Okay, and well, then they live exactly in f q the R multiplicative group. Okay, so now I claim that there is essentially no difference between this modified problem with prime and the original problem, and this is where we use the induction, because I say that the original zeta function is just the this new zeta function with prime times some extra factor, namely the exponent of the sum n r minus n r prime times t to the r over r. And this second factor, maybe let me call it z double prime. So z double prime equals the zeta function of the union of h I. So I goes from 1 to n, and this h I is just the intersection with the xi equals 0 hyperplane. Okay, so then it's just a tautology, and now the dimension of this is already n minus 2. Yeah, because we intersected a hypersurface like this of dimension n minus 1 with this hyperplane of dimension n minus 1, and then this z double prime is the product of the zeta functions of these codimension 2 varieties, but those codimension 2 varieties intersect in codimension 3, and so we will have to use this inclusion-exclusion formula and write it this way. So it's the product of usual zeta functions of h I t, the product over so it's product over I, and then now the product over I less than j zeta function of h I intersect h j t, and this is inverse. And then the product of over I less than j less than k zeta function of h I intersect h j intersect h k t, and so on. Okay, so if you know by induction that all the smaller usual zeta functions are meromorphic, then you see that the whole thing is meromorphic. So we reduced the problem to this prime zeta function. So suffices to consider or to prove the meromorphic property of zeta prime. Okay, and we'll do this. We said, well, q is some power, some prime power, and we fix some s. So we will consider q to the power s, that is p to the power rs, and then we will use this counting function, Gauss sum, and its Fourier transform, as I advertised many times before. So somehow this is the key moment of the whole the work argument. Okay, now it comes. So we want to compute some trigonometric sums. So recall that that we managed to write this down as the product of certain theta functions with good convergence properties of the Teichmuller representatives powers, say theta of p times so on times theta to a to p rs minus 1, like this. So here a lies in f q to the power s. Okay, and now we will use the following evident observation. Add one extra variable x0. So these run over FQS multiplicative group, and we sum up epsilon to the trace of x naught times f of x1 and so on xn. Okay, and then this equals q to the power s n prime s minus q to the power s minus 1 to the n for evident reason. Just since when we sum of the non-trivial character values over the whole group, we get 0. When we sum the trivial, what is f? Small f. This is the equation of our hypersurface. Just the thing we started with. Yeah. So it was hf, h sub f. Okay, so this is so because the sum over all x not in the multiplicative group of our field, epsilon to the power trace of x not times something is either -1 in case u is non-trivial, or 0 in case u is 0. Sorry, no, not 0, but when I will count q s minus 1 if u is 0. We'll just sum the units, as many units. Well, I'll write this. Okay. So we'll proceed with these two formulas. Okay, and now we replace all the coefficients in this expression x naught times f of x1 so on xn. So this originally was a polynomial over fq. But we replace all the coefficients by their Teichmuller representatives. Okay, and then we get well, so some function f over x0 and so on xn, and it will be a function over the Tate field, polynomial over Tate field, that we'll write as the sum of ai x to the wi. Just sum of monomials with these coefficients and with these powers. Okay. Yes. So just it was a polynomial, and now it had some coefficients. Maybe I should write so like this was equal to the sum of bi's x to the power wi, and then I said that ai is the representative of bi. Okay, so we get by this formula, because this inequality, say in complex numbers, if you wish, yeah, or in p-adic complex numbers in the Tate field. Okay, and so I will use this equality in the Tate field. So q to the power s n prime s is q to the power s minus 1 to the power n plus the sum over all x's in our FQS non-zero, the sum of epsilon to the power trace of x not f of x1 and so on xn, and this is equal to q to the s minus 1 to the power n plus the sum over all roots of unity of degree qs minus 1 over the products over I over theta over ai x to wi, then theta of ai to the power p x to the power p wi, and so on. And finally, theta of a to the power p to rs minus 1 x to the power p rs oh sorry, minus 1 is here, minus 1 these are all those pp powers times w. Okay, such a product. And now note that the coefficients of f were in fq, right? And q was p to the power r. And so this implies that for our Teichmuller representatives, ai to the p to the r is equal to ai. Okay. And now we set g is over x naught and so on, xn is such a product as here, just one sum. Does this. Okay. And then we get that q to the power s n prime s is q to the power s minus 1 power n plus sum over all non-zero coordinates. Yes. Yes, just one summand like this is called G. So I'm going to write here just the sum of G's. G of x times G of x to the q times G of x to the q s minus 1. Okay. Now recall that this theta function we used had some good convergence properties. So it all the factors here, like theta of ai to p to some power like m x p to m w I lied in this are not. So the formal series with good convergence properties in D of R bigger than so they were all convergent in the Euclidean disk, and in fact in the bigger disk. Okay, we proved this last week. And so it follows that the G function is also like this, since just the product of such series also lies in R naught. And then by the last time lemma, the corresponding trace was well defined. Namely, we conclude that what we're counting is just the is just the trace of psi to the power s operator, and psi was some composition of multiplication by g and so say loop rotation by q. Okay, so just the statement of lemma the previous time, and so from this we can express the desired quantity, the points in the away from zero hyperplanes, from the trace, and the trace, again, the very last lemma of the previous time was that the counting function of traces was the determinant of something. Now this determinant was meromorphic. So we are essentially done. Just let us do it formally. So we conclude that n prime s is a just I expand this by binomial formula. So we get the sum of n choose I, q to the power s n minus I minus 1, plus the sum from 0 to n plus 1 minus 1 to I, n plus 1 choose I, q to the power s n minus I, times trace of psi to power s. Okay, and now the counting function for n, the zeta function, will be the same as the counting function for psi, which will I just divide by this and expand those two by binomial formulas. So there is nothing interesting here. So we set delta of t is the determinant of 1 minus at, and this is the exponent of a negative sum of traces. Sorry. Okay, just as we did last time. And now we just plug in this expression into this formula, and we are done. For the last time, we also proved that this characteristic polynomial is a meromorphic function. Yes. Yes. So, what is t to the power s? Sorry. Thank you. Okay. So, what do we get? The desired zeta function is the exponent of the sum prime s t to the s over s, and this is the product from 0 to n of exponents of the sum of q to the power s n minus I minus 1 t to the s over s, and this is to the power negative 1 to the power I, and choose I. Okay, just exponentiate this equality, and times the product from 0 to n plus 1, the exponent of sum from 1 to infinity, q to the power s times n minus I, the trace of psi to the s, t to the s over s. Okay, and then this is to the power negative 1 to I, n plus 1, choose I. Okay, and this is the product from 0 to n of 1 minus u to the power n minus I minus 1 to the power minus 1 to I, and choose I, times the product from 0 to n plus 1, delta of q n minus I t to the power minus 1 to I plus 1 times n plus 1, choose I. Okay, and now here all the factors are meromorphic. So we are done. Okay, but as I yes, this we proved last time. The last lemma of last time. So Lemma said that such a characteristic polynomial is well defined, is convergent everywhere, and equals the exponential of trace function. So was this equality? There was this equality, and the statement that it makes sense, and is convergent everywhere as a series in T. Huh? Yes, certainly, yes. It's just definitions. So it is a formal. This thing is a formal series with coefficients in the Tate field. But not only this, we proved last time that it's not just formal; that it actually converges everywhere. So since this is a everywhere convergent power series, we now have a product of many such factors, but each factor is a formal power series convergent everywhere. So that's what we wanted to prove. So we realized the zeta function as a ratio of rational in the sense. No, I didn't prove that it's a ratio of two polynomials yet. No, I only proved that it's meromorphic. That it's a ratio of two power series convergent everywhere. And so I didn't finish yet with proof of the work theorem. It was the key point. All the rest will be sort of formality. The key point was here, and I confessed many times that I do not understand it. I asked Kaledin a few days ago, and he doesn't understand it either. So it seems nobody understands this. So formally, the work's argument looks like some computation in crystalline cohomology of the affine space. But nobody knows a clear explanation. At least no one of... I know nobody who knows a clear explanation. Okay. So once again, what we have achieved is the presentation of this formal series for zeta function as a ratio, as the ratio of two other series, but each of them is convergent everywhere. But we want to prove that the zeta function is the ratio of two polynomials. So we will need the following lemma. This sort of work criterion of rationality. And I'm not, in fact, I'm not even sure it's the work. Maybe it's like 100 years before, in 19th century. So I'm not sure. So we're given a function of, I mean, a formal series. And now the field is immaterial. It can be whatever you wish. Finite field, rational numbers, complex numbers, Tate field, whatever. And we want to check that this is a rational function. So I say that f is the ratio of two polynomials. If and only if the following criterion works. So there is some m and s positive integers such that the certain determinant and Sm will be 0 for any S big, maybe I should say capital S for any S bigger than capital S. So, in other words, for any big enough S. Now, what is NSM? NSM is the determinant of certain auxiliary matrix. And this auxiliary matrix is a Hankel matrix. So its diagonals, well, its anti-diagonals are constant. Namely, it is the matrix like this. A, these coefficients. S plus I plus J, okay, for So for example, let S be 0. Yeah. Then what do we get? If S is 0, we get just a 0, then A1, A1, then A2, 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 and so on. But it is M by M. And if S is not 0, well, it's just a S plus 1, a S plus 1, a S plus 2, a S plus 2, a S plus 2, and finally you will have a S plus M in the very end. Yes, I think it is. Yes, M plus 1 by M plus 1, right? Something's wrong? So, sorry, plus 2M minus 1. Yes, sorry. Yes. Thank you. But all the diagonals, all the anti-diagonals are constant. And maybe, yes? Maybe plus 2M. Yeah, because here you go to plus M. Yeah, maybe you're right again. Maybe plus 2M, yes. Thank you. And so maybe somebody knows this criterion by any chance, not yet, but it is a very useful criterion, and somehow it's okay if you forget everything else after this course is over. But if you remember this lemma and also Newton method of solving polynomial equations in Puiseux series, then I will not leave in wait. So these are the key points of this class. Oh, maybe I should. So maybe let's postpone the proof of this lemma for a while, and maybe let's use it and prove the rationality of zeta function. So prove later. And now use it. Prove rationality. Zeta function. Okay, so well, we have to recall the Weierstrass preparation theorem. So given a power series version everywhere, then for any radius r, there is a polynomial and a series with the constant term 1, such that f naught and f naught inverse both converge in D of R for this radius, this disk. And f equals this polynomial p times f naught. So this was more or less what we proved a month ago. And now let's write for the zeta function it's a meromorphic presentation. Okay, and let's take the radius, for example, q to the power 2n. N was our dimension. So hf was in a hypersurface. Okay, and apply Weierstrass theorem to this convergent power series, and we write in the form p of t, that's a polynomial. Pardon me, what is n? N is the dimension of hypersurface plus 1. Okay, so we apply it to the everywhere convergent function b of t. We say that it's a polynomial over some g of t. And g of t converges in d of r so we don't know yet that it's rational. A and B are both just formal series converging everywhere, and to one of them I apply the Weierstrass preparation theorem. So all in all, we get that this sorry, where is my f? This is a of t times g of t. So it converges in d of r as well. And f of t is also equal to p of t times the zeta function, just by construction. So let's introduce their coefficients. F of t is the sum of bi, t to the I, and it starts with 1. Now, p of t is a polynomial of degree e. Okay. And also, if it also starts with has constant term 1. Okay, and finally, our zeta function, we're interested in, has coefficients ai. And what is important is that all these coefficients are just, 1 plus t n of t. So what is important is that all the coefficients are positive integers. We'll use this essentially. Okay. Now recall that we proved this maybe a couple of weeks ago, that these positive integers are growing not very fast. Yeah, we argued that those coefficients, how to say it? If a variety contains some subvariety, then the coefficients for the ambient variety will be bigger than the coefficients for the subvariety. In particular, our hypersurface lies in the affine space, and these are coefficients for the affine space, and these are smaller. Okay. What else do we know? We also know that f of t converges in the disk of radius r. It was chosen q to the power 2n, and hence for big enough I, we have the p-adic value of the coefficients of bi are less than r to a negative I equals q to negative 2in. Case. Now I have to apply this abstract lemma. Compute those determinants. we will not be able to do the determinants certainly because we don't know anything exact about these coefficients, AI. But we'll be able to estimate those determinants. So one estimate will be just from this inequality. How to say? There's an Archimedean estimate. These are positive integers, so the determinants will be some integers, and we can just estimate their absolute value, just from this. On the other hand, from this, we'll be able to estimate the p-adic value. And those two estimates will be in sharp contrast. So they will not be able to coexist unless the determinant is just 0. Okay, we'll have an integer, a small integer with very big p-adic value, which is impossible. This is what we'll do. Okay, so we fix some m like here, like this m, which is bigger than twice e, and this e was the degree of our p polynomial. And set a Sm is the determinant. Well, is this matrix, Hankel matrix, As plus I plus J, where they both go from 0 to m, and the NSM is its determinant. So from the equality that f is equal to p times zeta, we get that b j plus e equals a j plus e plus c1 a j plus e minus 1 plus so on plus c0 aj. Sorry, it's not. It's CE. Sorry, CCE aj. Yes. Yes. But unfortunately, the f itself will change. You see, the f was taken from this Weierstrass preparation theorem, and the choice of f depends on R, on the disk. Also, yes, everything will change. Yes. Well, it will help in a few minutes, but okay. So we have this, and now take our matrix A Sm, and add well to each column starting with the last one, well, maybe to each j plus e column starting with the last one, and well, ending with the eth one from right to left. The linear, we add the linear combination of many previous columns with coefficients c k well times j plus e minus k column. So on the other hand, it will give us b. On the other hand, on the one hand, it will not change the determinant. So we obtain a new matrix A prime with the same determinant. And the first E columns of A prime are well equal to the first A column of A. Okay, but the last columns are well the same as in the corresponding B matrix. Maybe this. Just the one just the BSM is BS plus I plus J. Just from this equality, we use this equality to well rewrite the rightmost columns of A matrix as the columns of B matrix. The right half A we replaced by the right half of B. Now from this we will estimate the p-adic value of the determinant. So we know that the matrix coefficients of A are positive integers, and hence their p-adic value is at most 1. And now the determinant value is at most the maximum of value of B over J bigger than S plus E to the power of M plus 1 minus E. Yeah, because once again, the left part is an integer, and the right part coincides with B matrix. So I just estimated from knowledge of B, and we know that this is at most R to the power negative S m plus 1 minus e for big enough s. Yeah, because we know this. Okay. But now r was q to the power 2n, and m was chosen to be bigger than twice degree of p polynomial, and so we conclude that the absolute value of the determinant, p-adic absolute value, is less than q to the power negative ns times m plus 2. Okay. So this is the key computation. Now, what about the Archimedean? Absolute value over NSM. Well, the absolute value of NSM Archimedean is at most m plus 1 factorial, the number of summands in the determinant. And each particular summand is at most q to the power n s plus 2m m plus 1. Yeah, just because any element is at most this. Yes. Yes, but you see the A coefficients are just positive integers. It's zeta function, and we know that it counts number of points, and the number of points is a positive integer, and at most the number of points in the ambient vector space. So this makes some sense, and this estimate also makes sense. So now we'll just multiply those two estimates, NSM Archimedean value times NSM p-adic value is less than q to the power minus ns m plus 2 times m factorial. Sorry, what I'm saying, m plus 1 factorial times q to the power 2n m plus 1 times q to the power ns m plus 1, and this is m plus 1 factorial q to the power 2n m plus 1 over q to ns, and finally this is less than 1 for s big enough, and this cannot possibly happen unless this n is 0. Okay, that's it. So a very elegant but mysterious argument. And now we have to check this dilemma. It is rather straightforward in one direction. I mean, if you know that your function is the ratio of two polynomials, then those Hankel determinants eventually must vanish. I mean, if their size is big enough, and if they are far enough. This is easy, and the first statement is more tricky. So we'll start with the simple part. But anyway, this has nothing to do with p-adics. Yes, it's something absolutely algebraic. So in a sense, the p-adic course is over. Okay. So if f of t is rational, just again, let's write down explicitly that p of t is the sum of bi to the power I, q of t is the sum of ci t to the power I, and then take I bigger than the maximum of capital N, the degrees of these polynomials, f of t times q of t equals p of t, implies that the sum of I minus capital N plus j c n minus j is 0. Now just take this capital S the capital S was the shift to the right that guaranteed the annihilation of the determinant. So this pardon me? Yes. So yes, you're right. So take them as the maximum of n and n minus capital N plus 1 and 1, and take small m equal to capital N. And then we'll see that AS C n plus AS plus 1 C n minus 1 plus so on plus AS plus capital N C0 equals 0, AS plus 1 C capital N plus AS plus 2 C capital N minus 1 plus so on plus S plus capital N plus 1 C0 0 and so on. Finally AS plus capital N C capital N plus AS plus capital N plus 1 C capital N minus 1 plus so on plus AS plus 2 capital N C0 equals 0. Okay, so well, it has a solution. Hence the determinant must be okay. Now Well, the converse statement is, as I said, more tricky, and I will not have time to explain it. And somehow I'm in a stupid position because that's everything that remains. So if you wish, we can meet for like 10 minutes or 15 minutes next time, and I can explain it, or you can look it up by yourself, or even prove it by yourself. But somehow let me know. So I think that's the end. So if you wish me to finish the proof, I will be happy to do it next time. It'll take maximum of 15 minutes. Or if you don't want to come. You have it, what? Streamed, okay. Okay, so let's meet one more time, but maybe you'll have some questions, for example, whatever. So if nobody has any questions, I will just finish this argument, and that will be it. But if you have some suggestions, you are welcome. Yes. Let me look it up. I think it's open, but maybe I'm wrong. It's closed. It's closed. Sorry. Okay, so once again, if you have any suggestions for the next time, please write me an email. Otherwise, I'll just present the end of the proof, and that's it.